Section 5.3, Properties of Trigonometric Functions. So once we have the definitions of the trig functions based on the unit circle, a couple things happen. Well, first thing we just want to discuss, how do we determine the sign based on quadrant? Now this should be obvious, but because of our definitions based on the unit circle, then all we really have to do is look at the x-coordinates and the y-coordinates and whether they're positive or negative, and all of this is answered. So just as a refresher, quadrant 1, x and y are both positive. Quadrant 2, x is negative, y is positive. Quadrant 3, x is negative, y is negative. Quadrant 4, x is positive, y is negative. Well then, once you get there, of course, this is how we superimpose our unit circle onto the xy coordinate plane. Then when we rotate from standard position, we end up with a couple things. Well, in the first quadrant, no matter what you do, everything is going to be positive. And so a mnemonic that we're going to use, or that I use to help remember which is positive where, is all students take calculus. So let's run through this. So in quadrant 1, all the trig values are positive because, of course, y is positive, x is positive, x and y being divided still positive, y positive, x positive, y positive. Well, then you get to quadrant 2, and in quadrant 2 the x's are negative, and since the x's are negative, that means that cosine should be negative, tangent should be negative, secant should be negative, and cotangent should be negative. Now, I'm going to say S for the sine of angles in quadrant 2 are positive, but remember that sine and cosecant really, because of this definition, are directly related. So anytime we say that sine is positive, we automatically assume that cosecant has to be positive also. Then, in quadrant 3, both of them being negative, well, that means that sine is negative, cosine is negative, but tangent being the division of two negative numbers, that's going to give you a positive, and so we say that tangent of angles in quadrant 3 are positive, and of course, because of the relationship between tangent and cotangent, we're going to make the claim that anytime tangent is positive, cotangent is also positive. Then in quadrant 4, x being positive and y being negative, that means that sine is negative, cosine is positive, tangent is negative, cosecant is negative, secant is positive, and cotangent is negative, and then we're going to say cosine of the angles in quadrant 4 are positive, and of course, because cosine and secant are directly related by their definition, this holds for both of them. So all students take calculus, all students take classes, however you want to think of that, because you might not take calculus, but you're definitely taking classes, and so that's how I remember which quadrant gives you which positive trig functions. Now once we know all this, if we're given a little bit of information, then we can figure out where theta lies based on just if the trig values are positive or negative. So here they say specifically that sine is negative and cosine is positive. Well, let's remind ourselves, all of them are positive there. Sine and its reciprocal is positive there. Tangent and its reciprocal are positive there. Cosine and its reciprocal are positive there. So, if sine is negative, well, that means we're not in quadrant 1 or quadrant 2, so we're either in quadrant 3 or quadrant 4. But because cosine is positive, we know that we're in quadrant 4. Then, if cosine is negative, well, cosine being negative means we're either in quadrant 2 or quadrant 3. So, and tangent is positive, well, that answers that question. That automatically forces that we're in quadrant 3. Then, if cosine is positive, so that means we're on the right side. We're either in the all or the cosines area. And tangent is positive. Well, we know we have to be in quadrant 1. Then, if cosecant is positive, well, if nothing else, let's remember which one's which. Sine of theta is related to cosecant of theta. And so specifically, cosecant of theta is equal to 1 over y. And so cosecant being positive really also means that sine is positive. And so if sine is positive and cosine is negative, then that means we have to be in quadrant 2. Now this continues to be very important later on for when we start solving equations, and it also is important if we're trying to find all the trigonometric values based on just one or two trig values. So a really awesome thing that happens is that when we're dealing with this unit circle definition, it's pretty easy to see that, of course, we start from standard position, and then we do our rotations, right? So let's say I rotate to 90 degrees. Well, that's a 90-degree rotation. But remember, the truth is you could do more rotations than that, right? You can rotate all the way around and then come back, and that still ends up in the same place. How that applies for us is that two angles in standard position are said to be coterminal if they have the same terminal side. So that 90-degree angle and then that full rotation where we get 360 degrees plus a 90-degree angle, those things are what we call coterminal angles. Another example would be 120 degrees and negative 240, or 5 pi 6 and negative 7 pi 6. So, of course, what does a 120 degree angle look like? Well, if we start from standard position and we rotate to 120 degrees, then that's this right here. But if we were to do a negative 240 degree rotation, then we start here, we rotate, we go negative 240 degrees, and we end up in the same place. All right? And so these angles are coterminal. Now, what really matters is that they're a complete rotation away from each other. And so notice that if I erase everything and I just leave our terminal ray, well, all I've got to do is make a complete circle and I could get back there into these other degree units. 120 degrees minus 360 will actually give us negative 240. And similarly, you could have said 5 pi 6 minus 2 pi, because that's a full rotation, is actually negative 7 pi 6. Why should we care about coterminal angles? Well, we care because if we take the trig function values of a specific angle and any of their coterminal angles, we're going to get the exact same answer. That is, sine of 120 degrees is going to be equal to sine of negative 240 degrees, which is root 3 over 2. And so this is wonderful because that means that lots of angles that we may see, we could simplify them back to either between 0 degrees and 360 degrees or between 0 and 2 pi rotation, and everything can be brought back to a unit on this unit circle where the rotations are only one full revolution. And this makes everything so nice at certain times. Now there may be some situations where it makes us have a little more work to deal with, but it's also very helpful. Well, so let's say that we want to find the exact values of the following and we do not want to use a calculator. Well, I have a hint for you, and that hint is that you're going to add or subtract integer multiples of 2 pi or 360 degrees. Remember that an integer is just a positive or a negative counting number, including 0. So it could be negative 5, positive 3, and 0. Any of these are a multiple. So essentially, if you're trying to get these to inside one single rotation of the unit circle in the positive orientation, all you have to do is do a subtraction or an addition of 360 degrees or an addition or subtraction of 2 pi until you get something between 0 degrees and 360 degrees or 0 and 2 pi radians, and then you can calculate it based off this unit circle. So specifically, if I have sine of 390 degrees, well, if I take 390 degrees and I subtract 360 degrees, what am I going to get? Well, that's 30 degrees. And so my claim is that a 30-degree rotation is the same thing as a 390-degree rotation, but that can actually be confirmed because if I were to take and do a full rotation of 360 degrees and then do an additional 30 degrees, I'm going to land in the exact same place. So sine of 390 degrees is the same thing as sine of 30 degrees, which is of course 1/2. Then, if I have tangent of 19 pi fourths, well, let's do this. If I've got 19 pi fourths, I don't see that showing up on my unit circle. Notice that I've got up to 7 pi fourths because we can reduce this, and of course the other pi fourths iterations ends up on the quadrants as the quadrantial angles. But I can just subtract 2 pi from this and see if I can get further down. Well, subtracting 2 pi from this, I need a common denominator. My common denominator is 4. So multiply by 1 in disguise, and that's going to give me 19 minus 8, or 11 pi fourths. Well, 11 pi fourths still isn't on there, so let's subtract 2 pi again. Once again, 2 pi over 1, multiply by 1 in disguise, that's 4 over 4, and that's going to give me 3 pi fourths. And so specifically, I claim that 19 pi fourths is the same thing as 3 pi fourths. I see that 3 pi fourths is right here. And so then the tangent of 19 pi fourths I claim is the same thing as the tangent of 3 pi fourths, which is going to be negative 1. Then cosine of 10 pi thirds, we can play the same game. I don't see 10 pi thirds on my unit circle. So 10 pi thirds minus 2 pi over 1 multiplied by 1 in disguise, which is going to be 3 for my common denominator of 3. That's then going to be 10 minus 6 is 4 pi thirds. And look, I've got 4 pi thirds right here. And so I claim that cosine of 4 pi thirds is the same thing as cosine of 10 pi thirds, and that is negative 1/2. Then secant of negative 11 pi sixths. Well, notice in this situation, because it's negative, I'm actually going to add 2 pi to it so that I can get between 0 and 2 pi. And so negative 11 pi sixths, add 2 pi, multiply by 1 in disguise. 2 times 6 is 12. 12 minus 11 is 1, and so this is 1 pi sixth. Now, the truth is we could have done this either way. We see that our terminal ray is at pi 6 radians, but of course you could have done the negative rotation of negative 11 pi 6, and you of course would have ended up in the exact same location. But that's the beauty of this, is that it doesn't matter. You'll get the exact same answer, which is then secant of pi 6, which is 2 root 3 over 3 after rationalization. Now once we have this idea of coterminal angles, well, let's kind of generalize what all I just said. That is, if you let k, in my formula here, be an integer, so just for mathematical notation, usually a double script z means integers. And remember that the integers are the positive and negative counting numbers or whole numbers. Well, the deal here is that sine of some angle theta plus 2 pi times any integer, any whole number, positive or negative, is the exact same thing as sine of theta. Well, you can also do that with degrees, and so if you take some theta in degrees and you add 360 degrees times k to it, you're still going to get the exact same thing as sine of theta. In addition to that, of course, the same thing can be said about cosine, and I also claim that it's true that you can say the same thing about tangent, cotangent, secant, and cosecant for all the same reasons. But specifically, what does this do for us? Well, this creates what's called a periodic function. And so a function is going to be called periodic if there is a positive number p such that whenever theta is in the domain of the function, so is theta plus p, and specifically f of theta plus p has to equal f of theta. And so notice this is pretty much exactly what we've written here, and so that is trig functions create what are called periodic functions. They are periodic functions. Now specifically we're going to say that if there is a smallest number p, that is a smallest amount of change that's allowed that still keeps you with the same answer, we're going to say that that's the period. Now this idea of period is going to come up pretty heavily, but just understand that period is just what is the distance that you can add to your theta to get the exact same answer. And we know that one full rotation of a circle is going to be that period for sine and cosine, right? That's exactly what, once again, these two things say. You do a full rotation, you get the exact same answer. So we're going to actually extend this, and we're going to write down what is the period of each one of these trig functions. Now, for sine and cosine, we just addressed it. It has a period of 2 pi. Okay, and if you were in degrees, it's okay to use it in 360 degrees, but there's a reason that I'm mentioning the period in terms of radians, and that is specifically we are going to learn pretty soon how to graph these functions on an xy coordinate plane, and when we do, we're going to talk about our inputs being in radians, not in degrees. Alright, but tangent is a little different. And so remember that our definition of tangent is y divided by x. And so I want you to look at stuff on the unit circle. Well, remember that on the unit circle, up here, we have everything's positive, right? But specifically, if I'm trying to find tangent of something like 30 degrees, I would divide root 3 over 2 divided by a half. Or if I was trying to find tangent of 45 degrees, it would be root 2 over 2 divided by root 2 over 2, which would be 1. And then so on and so forth. Well, notice that if you're in quadrant 2, stuff is negative. But then if you get in quadrant 3, something weird happens. And so when you actually find tangent, notice that if I look at these two things here, and I divide root 3 over 2 divided by 1/2, that's the exact same thing as negative root 3 over 2 divided by negative 1/2, because they're both going to come out positive, right? Well, also, if I were to do pi fourths and 5 pi fourths, the same thing happens for tangent. And if I were to do pi thirds and 4 pi thirds, the same thing happens. And then honestly, it happens for each one of these, and notice that they're directly across from each other. Now, directly across from each other in terms of radians is pi radians, right? And so when I start looking at these values, what really happens is that I get the period of tangent is going to be pi radians. So every pi, tangent repeats. So it's a little bit tighter than sine cosine. Cosecant, secant, and cotangent, they're going to fall out immediately from sine, cosine, and tangent. Sine's period being 2 pi means that cosecant's period is 2 pi. Cosine's period being 2 pi means that secant's period is 2 pi. And the fact that tangent's period is pi means that cotangent's period is also pi. Once again, this just means that the exact same values that pop out of these trig functions repeat for every 2 pi radians or pi radians in the tangent and cotangent. Now that we have this idea, we actually want to address what is the domain and range of all our trigonometric functions. Now, as a reminder, when we talk about domain, what do we really mean? Well, first off, we mean the thing that gets plugged in. Okay? Now, I've got function f of x. What I really should have to match my notation is f of theta, since my input here is theta. Okay? But it doesn't really matter. It's just what's being plugged in. And so our domain is going to be the input values that make sense for a specific trig function. And I've written our definitions here to remind us. Well, from pre-cal, recall that the issues that we saw with domain really had to do with even index radicals. We don't have those problems here. And division by zero. And so division by zero is the one that's going to drive our domain restrictions. Well, notice that sine and cosine don't have actually any division, and since really I'm just looking for what is the theta measurement that's getting plugged in, if I ask the question what thetas can be plugged into sine, the answer is anything you want. And so we're going to say that the domain of sine is all real numbers. Sometimes that's also written in interval notation, that is from negative infinity to positive infinity, not including the endpoints because of course infinity aren't values, they're just ideas. Sometimes you may also see this double script r, and that just represents all the real numbers. Now, the next question we have is what is the output of sine? Now specifically the range means that if you could run through all the domain values, what would it look like? Which is why it's kind of easier to find range when we're dealing with the graph itself. But I actually claim that if we think about what's happening with sine, we can figure this out by just a little bit of thought. So specifically, from our definition, sine is just the y value. But notice that if you start here on the unit circle and you start rotating, the y value is going to change, right? Well, but here the y value is 0. Well, the y value is increasing, still positive, still positive, still positive, 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 but it tops out as a y value of 1. And as I keep following the unit circle, y values keep decreasing until we get to 0. Then they decrease and become negative, but they're decreasing until we get to negative 1. And then they start increasing again, but they're negative until we get back to 0. The y values, and I was literally just thinking about what was the y coordinate on the unit circle as I circled around, but notice that if I'm dealing with the y values on the unit circle, they're never going to be bigger than 1. They're never going to be smaller than negative 1. And since that's the case, I can claim that the range of sine is really going to be between negative 1 and 1, including those endpoints. Remember that the square brackets are inclusive, meaning including. Well then, to extend the concept, cosine is really not any different because, of course, via our definition here, you can plug in any angle you want and you will get a x value that makes sense. So the domain of cosine is all real numbers. And the range of cosine is similar to sine. I'm actually going to say it's the same, but for a slightly different reason. Remember, if we're looking at the x value, the x values are positive 1 here, decreasing, decreasing, decreasing to 0, decreasing, decreasing to negative 1, increasing to 0, increasing to positive 1. But if I keep following the circle, of course what happens? You'll never get a value smaller than negative 1 for the x. You'll never get a value larger than positive 1, and so I claim the range of cosine is negative 1 to 1. Now tangent is where we actually have to be concerned because we have division. And so notice that the problem is going to be anytime that x is 0, tangent breaks down. So how are we going to figure that out? Well, first off, let's see where is x 0. Well, x is 0 here and here, so these terminal rays are where tangent is 0. Specifically, that's going to be at pi halves and at 3 pi halves. Well, and then of course you could rotate more times and more times and more times and more times. Well, because of this periodic and this coterminal angle thing, we actually have to deal with every single iteration of pi halves and every single iteration of 3 pi halves that can show up. And so how are we going to say that? Well, we're going to first say let n be an integer. And then we're going to say that tangent can take in anything except pi halves plus n pi. And so pi halves plus pi ends up down here, right? And then plus pi again, plus pi again, plus pi again, plus pi again, plus pi again. So notice that what we just said was the easiest way to take care of all the situations where tangent's going to be 0, and that's going to be a pi halves plus iterations of pi, or subtract iterations of pi. Either way, you'll get that those are the problems. So domain of tangent, everything except pi halves plus n pi. Well then, the range. Well, this is a little bit trickier to deal with, but if you were to look at the division of these things and you do what's called analysis, then you could start taking and just kind of plug in the divisions and see what we get. But I claim that what you're actually going to get on the output of the tangent is literally everything. So the range of the tangent function is going to be from negative infinity to positive infinity. Anything could show up. Now, remember that our issues are division by 0, right? Well, when we do our cosecant definition, the fact that we're dividing by y, anywhere that y is 0 breaks. And so y is 0 where? It's going to be 0 here and here. Alright? So that's where we have problems. These terminal rays. And so that means we're going to have to deal with the fact that anytime we have an iteration of pi, and so notice that once again n is an integer, cosecant can take in anything except 0 or pi or iterations of that. Well, since n, being an integer, n could be 0, 0 times pi is 0, and so that takes care of itself, right? And then, of course, pi plus pi plus pi plus pi plus pi plus pi plus pi. Okay? Every one of those is out. Now, the range is a little bit weird, but I claim that if you consider the fact that it's just 1 divided by the y coordinate, alright, so over here it's undefined, right? But then what's 1 divided by a really, 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 really tiny number? Well, it's going to be a really, really, really big number. And then as you keep moving, you get closer and closer and closer to 1. And 1 divided by 1 is going to be 1. And then you make that same circle back again. This one actually matches that side. This one's undefined, of course. But then you get to the negatives, and so then you get negative values that are really, really big, all the way down to 1 divided by negative 1, which is negative 1. So what is the range of cosecant for all of this that I just said? Well, what's going to happen is you're really going to have from negative infinity up to negative 1, and it's going to include negative 1. But then you're going to have a weird gap. There's not going to be any values that pop out between negative 1 and 1, and then you'll pick back up at 1, and then you'll continue forever up. And so cosecant is going to have the range of from negative infinity to negative 1, union, in 1 to infinity, and it is inclusive on that negative 1 and 1. Those values do show up. Now secant, notice that secant is division by x. Well, that's really the exact same thing as division by x in the tangent. So I claim that the domain of secant actually is the exact same domain as the domain of tangent for the exact same reason. Division by x is where it breaks. But when we're talking about range, secant and cosecant, their range ends up being the same. For similar arguments, you're just swapping the x's and the y's. And so for the range of secant, it is from negative infinity to negative 1, including 1, negative 1, union, including 1 up to infinity. And then notice that when you get to cotangent, cotangent and cosecant have the same division by y, and so cotangent and cosecant have the same domain. They have the same restrictions, and then the cotangent range is really the same as tangent, which is all real numbers. Now we need to give another definition, and we're going to call this identities. And so specifically an identity is an equation that is true for all possible values of the variables. And so I claim that technically we already have some identities. If you wanted to think of it, the definitions that we have, those would be identities. The coterminal statements that we made earlier, those are now identities. They are always true. We're going to get several more. These are the reciprocal identities. But specifically, they are the idea that if you're trying to think of cosecant, it's okay for you to think of cosecant as really just 1 divided by sine. You use the definitions and you get it. Well, secant of theta is going to be the same thing as 1 divided by cosine of theta, and tangent and cotangent of theta is 1 divided by tangent of theta. Well, of course, you could do a little bit of algebra, and it is also true that sine of theta is equal to 1 over cosecant when we're dealing with certain things, but of course you have weird domain restrictions that occur, so it's a little bit of odd stuff that happens, but it's still possible for you to write these other reciprocal identities. Then we can also use those same definitions to think of tangent of theta is really the exact same thing as sine of theta over cosine of theta, and cotangent of theta is the exact same thing as cosine theta over sine of theta. Now, we'll see that these can be very helpful later on, but they're really coming directly from the definitions that we gave for our trigonometric values. So now what I want to do is I want to use the trig identities to actually find these values. And so given that sine of theta is equal to square root of 10 divided by 10, cosine of theta is equal to negative 3 root 10 over 10, we want to find the exact value for the 4 remaining trigonometric functions. Well, the beauty of the identities is that sine of theta automatically gives us cosecant of theta. Because, of course, cosecant of theta is 1 over sine of theta. That is, you just take the reciprocal, and that's going to be 10 over root 10. If you need to rationalize, that's fine. It ends up being 10 root 10 divided by 10. And then, of course, because cosine of theta is equal to negative 3 root 10 over 10, then secant of theta, being 1 over cosine of theta, is then going to be negative 10 over 3 root 10. Or you could rationalize, and that would be 10 root 10 over 3 times 10, but that would reduce, and that ends up being root 10 over 3. Watch my typo. It was negative, and so it has to remain negative. So I've got cosecant, I've got secant. Well, then how can we find tangent? Well, since tangent of theta is the same thing as sine of theta over cosine of theta, then that's going to be root 10 over 10 divided by 3 root 10 over 10, negative, which then becomes fraction multiplication, which is then root 10 over 10 times negative 10 over 3 root 10. Root 10 divided by root 10 is 1, 10 divided by 10 is 1, and we're left with negative 1/3, and so that is tangent of theta. Then, of course, cotangent of theta. Well, at this point, you could use one of two identities. You could either use the reciprocal identity, which actually is what I'm going to do, or you could use cosine divided by sine and get the exact same thing. But I'm going to use the reciprocal identity, that is 1 over tangent of theta, which is, of course, going to be negative 3 over 1, or negative 3. Well, then we get some more identities. So specifically, we get the Pythagorean identity. Well, what is the Pythagorean identity? Well, specifically, think about Pythagorean theorem. X squared plus y squared is equal to the hypotenuse squared. But remember that unit circle that we generalized and we made it not a unit circle, we just said for any circle? We get that x squared plus y squared equals r squared based on a right triangle. Well, this is literally where the Pythagorean identities come from. You just do it on the unit circle. So if the radius is 1, r is 1, and then x is cosine and y is sine. And since that's the case, we actually get this identity, sine squared theta plus cosine squared theta is equal to 1. This is true because of Pythagorean theorem. Well, then if you want, you can do some algebra to this, and you can find a few different iterations of the Pythagorean identity. We're just doing algebra here. So you can divide all three of these things by the same thing. Specifically, I want to divide everything by cosine squared of theta. Alright, but then I want to use these identities we talked about earlier to simplify these things. Well, before we simplify, cosine squared theta divided by cosine squared theta, that's just 1, right? So that's 1. 1 divided by cosine squared theta, that's actually going to be a reciprocal identity. Cosine squared theta in the denominator would be the exact same thing as secant squared theta. And then sine squared theta divided by cosine squared theta, well, that's really tangent squared theta, right? And so using the other identities, we get this one. Tangent squared theta plus 1 is equal to secant squared theta. You really only have to remember sine squared theta plus cosine squared theta is equal to 1, and you can get all the other ones. Well, I claim just like we divided by cosine to get that second one, we could also divide by sine squared. And sine squared of theta divided by sine squared of theta is 1. Cosine squared theta divided by sine squared of theta is going to be cotangent squared of theta. And then 1 divided by sine squared of theta, that's cosecant squared of theta. And so we get 3 iterations of the Pythagorean identities, noticing that sometimes you can replace one with the other. Now, of course, because these things are identities, that is, they are equations that are always true, we can also do algebra to them. And so if you wanted, you could solve for sine squared by saying things like minus cosine squared theta minus cosine squared theta, just doing some algebra, and you could also get that sine squared theta is equal to 1 minus cosine squared theta. So the truth is you have lots of possibilities on what you can do, but to minimize your memorization, just notice some of these tricks I'm playing and see if it helps you. But you can then do algebra to all of these when necessary to get some equivalent identity. So now that we have identities, we can approach these, find the exact values given a little bit of information in 2 ways. We can use the unit circle just like we learned originally, and we can also use all the identities. And so just in the spirit of doing them 2 ways, the first one I'm going to use strictly the information that we know from geometry or about our circles. But before we go further, we do have to figure out what. But we're told that theta lives between pi and 3 pi halves. Theta living there means we're actually in quadrant 3. Now, why is that useful? Well, first off, it tells me that I know that my ray has to be here. Well, if that's the ray, then my circle looks like this. And then the fact that I've got the definition of sine of theta being equal to y divided by r, knowing that I'm in quadrant 3 means that my x value is negative and my y value is negative, and so my r is positive, and so I'm going to rewrite negative 2/3 as negative 2 over 3. My radius is 3, and then I can find my x and y coordinate. Specifically, I've already got my y to be negative 2, but then I need the Pythagorean theorem to find my x coordinate. X squared plus negative 2 squared is equal to r squared, or 3 squared. And so x squared plus 4 is equal to 9, minus 4 minus 4. X squared is equal to 5. Take the square root of both sides. That's negative root 5, because specifically we know our x's are negative. So you have to make sure you understand that, yeah, when we take the square root of a square, you've got to make a discussion, have the discussion, is it positive or negative? Alright, so then, using our circle and our definitions, we've now got everything else. We get cosine of theta is x over r, or negative root 5 divided by 3. We get that tangent of theta is equal to y divided by r, or negative 2 divided by negative root 5. And if you needed to rationalize, multiply by root 5 over root 5. Negative divided by negative is going to give us positive, and then 2 root 5 is 2 root 5. Root 5 times root 5 is just 5, and so there's tangent. So we've got cosine of theta, tangent of theta. Cosecant of theta, well, of course, if we were using the identities at this moment, we could do the reciprocal, but in the spirit of using the circle, that's going to be r over y, or 3 over negative 2. Secant of theta is r over x, or 3 over negative root 5. Then to rationalize, multiply by root 5 over root 5. That's going to be 3 root 5. It is negative over 5. So there's secant of theta. And cotangent of theta is x over y, or negative root 5 divided by negative 2, which is positive root 5 over 2. Now, just as a quick reminder, just to verify, which trig function should be positive in the third quadrant? Well, tangent and its reciprocal function should be tangent positive, cotangent positive, everything else is negative. That works out exactly like we wanted it to. Now, using identities, all the identities we just learned, we don't have to do any of this unit circle stuff. You could use a mix. Now, but just for the sake of seeing it, let's use the identities. And so, if I'm told that sine of theta is equal to negative 2/3, well, of course I get one for free, and that's cosecant. Cosecant of theta via the reciprocal identity is just negative 3/2. We get those. All right. Then what else can we get? Well, now we have to use an identity. And so he's going to use the Pythagorean identity. Sine squared of theta plus cosine squared of theta is equal to 1. Before I go further, let's have a discussion about notation. And so when we write sine squared of theta, what do we actually mean? Well, we actually mean take the sine function of theta, whatever that value is, and square the entire thing. That's just our shorthand notation for it. Cosine squared and all the other squares all mean that same thing. You're just squaring the entire trig function. So then, when I replace sine of theta, what that looks like is negative 2/3 quantity squared plus cosine squared of theta is equal to 1. And so now I can solve for cosine of theta using algebra. That's going to be 4/9 plus cosine squared of theta is equal to 1, minus 4/9 minus 4/9. That gives me that cosine squared of theta is equal to 5/9. And then I can take the square root of both sides. Well, of course, we have to have the analysis discussion. The square root of cosine squared could be positive or negative. But we know we are in the third quadrant. And since we're in the third quadrant, we can say, oh, well, I know that means I have to take the negative version. So cosine of theta is then equal to negative root 5. Square root of 9 is 3. And so now I've got cosine of theta. So what's missing? Well, we get secant of theta for free. That's going to be negative 3 over root 5. And if we need to rationalize, multiply times root 5 divided by root 5, which then gives us negative 3 root 5 divided by 5. And then we can find tangent and cotangent by using the quotient identity. So tangent of theta is really sine of theta over cosine of theta, so that's negative 2 over 3 divided by negative root 5 over 3. Fraction division is fraction multiplication. Negative divided by negative is positive. That's then 2/3 times 3 over root 5, which is then going to be 3 divided by 3 is 1, 2 over root 5, or if you need to rationalize, multiply by root 5 over root 5. That gives us 2 root 5 divided by 5. And so 2 root 5 divided by 5 is tangent. And then I'm going to use this version right here as the reciprocal to find cotangent, since I get to do the identities. So then cotangent of theta is actually going to be root 5 divided by 2. Notice that if you compare all the answers we just found to the ones we found using the circle, they are identical. And so the identities are just as good as the circle. Let's do it one more time. Given that tangent of theta is equal to half and sine of theta is negative, we know that we have to be in quadrant 3 again. So sine is negative, tangent is positive. The only place that can happen is in quadrant 3. And so then we can use the unit circle again. So tangent of theta, that actually gives us way more information than we did before. Knowing that we're in quadrant 3, then we get the x and the y values. I just have to make them negative. Tangent is y over x, so that's going to be 1 and 2. And then using the fact that 1 squared plus 2 squared is equal to r squared. 1 squared is 1, 2 squared is 4, 4 plus 1 is 5. That gives us that r squared is equal to 5. Take the square root of both sides. Since this should have been negative because we know we're in quadrant 3. Then we get that r is root 5. So then we get all our other ones. Sine of theta is going to be equal to y over r, negative 1 divided by root 5, which then rationalizes as negative root 5 over 5. Cosine of theta is then negative 2 divided by the radius root 5. Rationalization gives us negative 2 root 5 over 5. We have tangent. Cosecant is then going to be root 5 divided by the y-coordinate, negative 1, or negative root 5. Secant is then going to be the radius over x, so that's root 5 divided by negative 2. Then cotangent is x over y, or negative 2 over negative 1, which is positive 2. And then for trig identities, then of course we get cotangent for free. Cotangent of theta is equal to 2 over 1 or 2. We can also use the Pythagorean identity that has tangent in it. So I remember that the primary Pythagorean identity is sine squared theta plus cosine squared theta is equal to 1. So we can find tangent squared theta by sine over cosine, so divide everything by cosine squared of theta. So sine squared of theta divided by cosine squared of theta is tangent squared theta. Cosine squared theta divided by cosine squared theta is 1. And 1 over cosine squared of theta is secant squared theta. So then using that identity, tangent squared theta, that's going to be 1/2 squared plus 1 is equal to secant squared theta. 1/2 squared is 1/4 plus 1 is equal to secant squared theta. 1 plus 1/4 multiplied by 1 in disguise. That's going to give me 5/4 is equal to secant squared theta. Take the square root of both sides. With square root of a square, we've got to be concerned about the positive or the negative. But because we know that we're in quadrant 3, we know that secant will have to be negative. And so we know that this has to be negative root 5 over 4, or secant of theta is really negative root 5 divided by 2, which then, of course, gives us cosine for free. Using the reciprocal identities, that's going to be negative 2 over root 5, or negative 2 root 5 over 5. Then all that's left to find is sine and cosecant. So I'm going to play a trick here, and I know that tangent of theta is equal to sine of theta divided by cosine of theta. And so I can actually make a new identity. I'm going to multiply both sides by cosine of theta. And I get that sine of theta is equal to tangent of theta times cosine of theta. Then Sine of theta is equal to tangent of theta times cosine of theta. Tangent of theta is a half. Cosine of theta is negative 2 root 5 divided by 5. Well, 2 divided by 2 is 1. I'm left with negative root 5 over 5. And then lastly, I get cosecant for free. Cosecant is then going to be negative 5 over root 5. Then if I need to rationalize is negative 5 root 5 over 5, but that reduces to negative root 5. And so then we have found them in two ways. Some more identities, even and odd identities. Now, recall that we have even functions if we have f of negative x is equal to f of x, and we have odd functions if f of negative x is equal to negative f of x. Now, if nothing else, also recall that even functions are the same thing as y-axis symmetry. This will matter later. And odd functions are origin symmetry. But origin symmetric or odd functions are f of negative x is equal to negative f of x. Well, the truth is that where does this come from? If you're thinking about our unit circle definitions, and then you flip across the x-axis, notice that the x values don't change. It's not the reflection that matters, it's that the x values don't change. And so negative theta is the same thing as positive theta for one of the functions, specifically the ones that are related to x. Well, which one are those? That's the cosine functions. And so I'm actually going to be able to say that cosine of negative theta is cosine of theta. Then, if you were to play with the other directions, you could get that sine of negative theta is equal to negative sine of theta. And so specifically, sine is odd function, cosine is an even function. Tangent, you can actually use the other identities to get that tangent of negative theta is the same thing as negative tangent of theta, which means then that it's an odd function. And then, of course, secant, cosecant, and cotangent pop out for free. Cosecant's the same as sine, that is, they're odd. Secant is the same thing as cosine, and therefore it's even. Cotangent is the same as tangent, so it's an odd function. If you have negative angles in some of these trig values, they simplify very nicely. And so for cosine and secant, the negative really can just go away. For the odd functions, you can pull it outside. So let's actually try this. So if I have cosine of negative 60, the fact that cosine is an even function means that this is really the exact same thing as cosine of 60 degrees. Then we just have to evaluate cosine of 60 degrees, which is 1/2. There we are. Well, sine of negative 420 degrees, sine is an odd function. That means that sine of negative 420 is the same thing as negative sine of 420. Well then, if you want, you could use the fact that 420 degrees positive is the exact same thing as a coterminal angle of 60 degrees, and then negative sine of 60 degrees is the same thing as negative square root of 3 over 2. Well, we've got tangent of negative 37 pi fourths. That is an odd function, so that's the same thing as negative tangent of 37 pi fourths. Then you can use coterminal angles, and you can find that 37 pi fourths is actually 5 pi fourths. And then negative tangent of 5 pi fourths is negative 1. Now, just using some identities, we're going to use the ones we know, and we're going to try to find the exact value of these trigonometric statements. So I've got secant squared of 18 degrees minus tangent squared of 18 degrees. And I want to use the identity that has to do with tangent squared and secant squared. So now the Pythagorean identity that I want to use is tangent squared theta plus 1 is equal to secant squared theta. Well, is there any way to get secant squared minus tangent squared? Well, sure. Subtract tangent squared theta from both sides. This is an equation. And so I get that 1 is equal to secant squared theta minus tangent squared theta. And the fact that my thetas match here, 18 degrees and 18 degrees, secant squared theta minus tangent squared theta, or secant squared of 18 degrees minus tangent squared of 18 degrees, must be 1. If I have tangent of 10 degrees times cotangent of 10 degrees, this might be easier to see if we use the reciprocal identities. So, tangent of 10 degrees times, well, cotangent of 10 degrees is really the same thing as, remember, if I have cotangent of theta, that's the same thing as 1 over tangent of theta. And so this is the same thing as 1 over tangent of 10 degrees. Well, tangent of 10 degrees times 1 over tangent of 10 degrees is tangent of 10 degrees divided by tangent of 10 degrees, and that's 1. And so that's the exact value. If I have cotangent of 20 degrees minus cosine of 20 degrees over sine of 20 degrees, well, what can we do here? Well, I know that if I have cosine of theta divided by sine of theta, that's the exact same thing as cotangent of theta, which means that this is then cotangent of 20 degrees minus cotangent of 20 degrees. Anything subtracting itself, that's 0. So my solution is 0. Tangent of 200 degrees times cotangent of 20 degrees. Okay, now it's a little weird, but let's see what we could do. Well, I know that cotangent of theta is 1 over tangent of theta. Alright, that's great and wonderful. But what is that going to do for us? I still have tangent of 200 degrees times 1 over tangent of 20 degrees. That 20 and that 200 are mismatched. I need them to be the same. Okay, well, let's think about something. Where is 200 degrees? Well, 200 degrees of rotation, that's 180 and a little bit of rotation. That is a 200 degree rotation. Ooh, I remember something. I remember when we talked about period, that the period of tangent is actually pi, or 180 degrees, which means that I want to know what is this angle, because the fact that that tangent has a period of 180 degrees or pi, I think I could rewrite tangent of 200 degrees. Well, specifically subtract 180 degrees from 200. 200 degrees minus 180 degrees. Well, that's going to be 20 degrees. There it is. That's the trick. We needed to know about the period. So then I know that tangent of 200 degrees is identical to tangent of 20 degrees, and then it's times 1 over tangent of 20 degrees, which is, of course, 1.